Hey guys, Kenna again. Like our last video on reflection, this one's going to be done a little darker, so it might be a little grainy. That's so that you can see the light beams better. Okay. Last time we were looking at mirrors and reflection. Today I want to go ahead and talk a little bit about lenses and refraction. So when we start thinking about reflection, remember reflection is a bouncing, whereas in this case we're dealing with refraction, which is a bending. Okay, so in reflection, you're causing it to bounce back off the surface. In refraction, it's going into a new medium. And when it does that, the speed of light through that medium is going to change. And with that change, as you change angles, that's going to cause the light to bend. You've already seen this effect with a water glass and a pencil going through it, but I wanted to go ahead and kind of show you this with more traditional kind of blackboard optics is what we would go ahead and do. So I'll start out with a polycarbonate or some sort of plastic in terms of the material that's going to slow it down. I'm going to start out with a rectangular shaped one. You can see it here. And we're going to go ahead and put this into our single light beam. Now, if I go in perpendicular, you're going to notice that almost nothing changes. Okay, the reason for that is, again, angle of attack is going to impact the bending of the light. Okay, this is where Snell's Law comes in. Now, if I start to change this, you'll notice that some of the light is actually being reflected. Okay, but if we think about where this was to start with, if we have it straight on again, I will go ahead and mark. This is left-handed, so I don't know how well I'll mark the level of where the light ray is coming out. Okay, now when I go ahead and start to bend it, hopefully you can see that as this angle gets steeper over here and some of that light is getting reflected off, the light that does come in goes through the prism, this prismatic glass, and then comes out the other side. But notice that there's a gap here. Okay, we are no longer coming out straight on from where the light was. Now we are coming out at a lower spot because the speed of light that traveled through here actually caused it to bend away from the normal. And then when it did hit this surface, changing from the plastic to the air again, now it changes one more time. And so you're actually seeing a change in the angle here where it strikes, and a change in the angle here where it exits. Okay, and I could keep going ahead and moving this, and probably better to show you kind of from on top if we can. All right, but as I do this, you know, the more I tip this block, the more it moves from that position. Okay, and this has to do with the thickness or amount of material that the light beam has to actually travel through. Okay. Now, we can do a little bit of this differently as we go ahead and start looking at in the corner here. This is an interesting phenomenon. You'll notice that there's actually no light coming out the other side. We have some reflecting off the top of the surface, you see here, and then some passing in, but when it passes in, it hits this barrier and it reflects back in this way. This is something called total internal reflection. Okay, total internal reflection, where the change in speed is so much that when you get to this interface between the air and the material, it can't escape and it bounces back in. And that ends up being pretty important when we start talking about things like fiber optics. Okay, you use the cladding in fiber optics to go ahead and allow that to bounce back through and stay in the core of the material to help transmit signals in that particular case. Okay, so we'll go ahead and put this particular one away, and then we'll go ahead and look at some other shapes. I have a triangular piece and I have a half circle, so we can go ahead and explore those really briefly before we move on to some other things. So again, this one, because the thickness, if I can pull it straight on, doesn't really change it, although you'll see a little bit of that trouble with escaping at that point. Okay, you can see that there's a fair amount of bend on this side in terms of refraction. Again, just following Snell's Law. Angle in, this will change depending on the N value for this particular material. We can go ahead and start turning it. You can see some reflection coming off and then again coming back down here increasing amount of refraction as it moves away from that horizontal line. Okay, but essentially the same properties we were dealing with the square are working out here with the triangle. Okay, so again, reflection off the surface, refraction as we're going through, changing from one medium to the next medium, and then when we exit again, changing from this medium to that medium, and we can calculate both of these using Snell's law. Okay, let's go ahead and switch. There's our circle, but again, you're noticing hopefully that it's the same sort of thing. Okay, you got your reflection coming off here, and your angle as it goes ahead and goes through is a bending because of refraction. Okay, depending on the thickness of the material. Oh, we reached a point of total internal reflection. You'll notice that no light is coming out here again, but we now have the primary ray bouncing back through the material. You'll notice up here it is exiting out. This is not so steep an angle that it can't get out, so it does escape on this side, but you get that internal reflection, okay, rather than the typical refraction. And as we go ahead and start moving back, all right, you can see all of that happening. You're seeing in here, there's a little bit coming out, but you've also got most of it being reflected, and then it escapes here as well. So there are a lot of interesting things you can do with this kind of material, but the one I wanted to focus a little bit on is lenses. Now, when we go ahead and start dealing with lenses, there are two typical types of lenses we want to go ahead and talk about. First is what we would call a diverging lens, and then what we would call a converging lens. So these are, I'll put them together so that you can behave like a single thing block for this first one. It's not perfect because there'll be an air gap, but you can see that for the most part, this essentially behaves just like our rectangle we had before. Now, when we go ahead and start doing this with these singular ones, this, right at this point, okay, is what we would call a diverging lens. And hopefully you can see that I'm not straight on center. Okay, so there's straight on center, pretty close. As I go ahead and pull this material, okay, this is going to get thicker and thicker, and hopefully you can start seeing what's happening to that light ray. Okay, as we go ahead and get to the thicker and thicker portion of this, the light ray is bending an increasing amount, and that's true whether we go down like this or we go ahead and push it up like this. The longer it spends in the material rather than in the air, it slows down and bends the light ray. Now, which direction depends on that angle of incidence. Okay, so like reflection that we talked about, angle of incidence matters, and that's going to be able to be used in Snell's law. Now, when we go ahead and start looking at this from perspective of this one, we have a very similar effect. If I can find dead center, okay, you'll see again it's lined up. As I go ahead and pull it, because it's going through less material, you'll see that it's going to go ahead and start bending. And as I go ahead and go back to middle, and then it's going through less material, which is causing it to bend. So in this one, if I start out in that middle point, pretty close here, if I pull it down, what direction does it go? Okay, it's going down because the material is getting thinner. Okay, as I push it back up, it starts going up. As I push this down, the material is getting thinner, so it's going to go up. Okay, again, that's because of angle of incidence. If we do that with the diverging, okay, we'll start here in the middle, pretty close. Okay, as I pull down, it's going up. As I push up, it's going down. Okay, so down goes up goes down. Down goes down, up goes up. Because of where the thickness is, these two are going to behave oppositely. Now, this is where we start wanting to go ahead and see that third ray and see what happens to multiple rays. Again, this is largely related to angle of incidence and what that does with Snell's law. So if we go ahead and start looking at our rectangle again that we started with, this is going to behave very much the same way as our flat mirror does, because the surface of interaction is essentially going to have the same angle in, therefore the same angle out in terms of reflection, same angle in, so same amount of bending through the material because of Snell's law. The end value for this material isn't going to change, so the angle that it comes in is going to determine how much it bends and what the angle is when it exits on the other side. Okay, so that's important to keep in mind, because when we change that thickness, we start thinking about how lenses work. Now, I'm going to go ahead and start with a converging lens. Okay, now as we go ahead and start looking at this, I don't know if we can get enough distance out of this, and this works much better if you have two, although this isn't realistic. Your glasses wouldn't actually look like this. I suppose they could. But if we go ahead and use two curves, you'll notice that what happens to that light ray. Okay, those light rays are coming together or converging. This is a biconvex, right? This is the typical type of glasses. I'll start standing up, see if you can see that a little better. Okay, so you can see that the light ray are coming together. Okay, so again, those light rays are coming together. So you have these two converging lenses, and when we go ahead and start looking at this, this is the kind of thing that you would typically use. Sorry, I'm sitting back down again. This is the typical thing you would use when you're dealing with somebody that has a hyperopia or farsightedness. But with somebody who has nearsightedness or myopia, you're typically going to use a diverging lens. And I don't have a double of this for you to see the effect as much, but you can see it with just one, and you can see that these waves are beginning to, these light rays, not waves, are beginning to separate. So if we take it off, then we put it in, you'll notice that their outer rays are starting to separate. Okay, you can still get that bending, but typically when you wear contacts or glasses, you wear them straight over the front, and you'll notice that they're separating here. Now, why would we use these two different ones? When we go ahead and start looking at somebody who has nearsightedness, like I do, myopia, what's happening is your natural eye is focusing light in front of the retina. And so when we start putting it in front of the retina, we want it to be directly on the retina, so we need to move those light rays back, which is why you would use a diverging lens, like we have here, to move the focal point further back to have it land on the retina. When you have somebody who has hyperopia, remember your normal lens is going to be curved like this, the shape of the eyeball. We go ahead and put that other lens on it so that we can go ahead and converge those rays. And when we go ahead and converge those rays, that works because somebody that has hyperopia is going to go ahead and have the focal point behind the retina. And we want to go ahead and move it forward so that it again sits right on the retina. Okay, so these are the types of things we need to make sure we understand about with respect to lenses and how they change the travel of light as it goes through them. So when we have a curved lens, this is converging. This is going to cause the light rays to come together. When you have a concave lens like this, you're going to go ahead and cause the rays to diverge, and that's going to change your focal point when we deal with glasses. We also use this type of technology when we do telescopes, when we go ahead and use microscopes, but it's all about how we change how the light moves to go ahead and get objects to magnify, to get objects to make them upright, these types of things. And so that's why it's important to keep track of those properties, whether it's upright or inverted, whether it's a real or virtual image, or whether it's magnified or diminished. All of those are with respect to how the light travels, whether it travels through any other materials, lenses, etc., to go ahead and change the way you see an image. This week, we will go ahead and talk about mirages, which is one application of some of what you're seeing here, that is not using a lens or that type of material to go ahead and change the behavior of light. Okay, thank you guys. I hope you had got some information out of this and it was useful for you. I'll talk to you soon. Bye.